Hey everyone, and welcome to today's Explainer. We hear a ton about massive, large language models these days, but today we're going to pull back the curtain and unravel the fascinating and honestly beautiful math behind how machines actually learn to predict human language. Beneath all the hype, regardless of a model's size, they all share a remarkably elegant mathematical foundation, and we're going to break it all down together. Okay, let's start with a quick little test. Think about this for a second. How would you complete this sentence? The water of Walden Pond is so beautifully, you intuitively guessed blue, right? Or maybe clear. You definitely didn't think of the word refrigerator. And you know what? That proves that you naturally possess a powerful internal language model. Your brain is already doing exactly what we train these computer systems to do.
So here's our roadmap for today. We'll be looking at predicting the next word, the n-gram shortcut, testing and perplexity, the zero problem, and finally, smoothing the probabilities. Let's just dive right in.
All right, part one, predicting the next word. This is literally the core problem of all language models.
Whether a model is just correcting your grammar, fixing typos in a text, or powering life-changing assistive communication devices, fundamentally, they're all built just by training them to guess the upcoming word. It sounds almost too simple, but this prediction engine is the absolute beating heart of natural language processing. Now, our immediate instinct to solve this might be to just take a massive database of text and count every single time a specific full sentence occurs. Like, just count how many times an exact 20-word history was followed by blue versus red. But there's no way that works. Human language is way too creative and infinite. Think about it. Most of the sentences you'll say today have literally never been spoken before in that exact sequence.
Which brings us to part two, the n-gram shortcut. This is how we actually make the math possible.
Since we obviously can't count every sentence in existence, we kind of hit a roadblock. But thankfully, there is a brilliant mathematical shortcut. The crucial realization here is that we don't actually need to look at the entire sentence history. We can approximate it by just looking at the last few words. In math, this is known as a Markov assumption. We basically assume that the immediate past is enough to predict the immediate future. And that brings us to the n-gram. This is what allows us to take the infinite complexity of language and break it down into manageable 2- or 3-word chunks. An n-gram is simply a sequence of n words. So a bigram is 2 words, like the water. A trigram is 3 words, like the water of. By shrinking our focus down to this tiny window, we can finally start counting sequences that actually reliably repeat.
And honestly, the math here is beautifully simple. It perfectly illustrates what we call maximum likelihood estimation. We get to avoid terrifying complex equations and just use basic fractions to determine the probability of the next word. You literally just find a prefix word, count how often your target next word follows it in your data, and divide that by the total times you saw the prefix. Boom. It is wonderfully straightforward.
Moving on to part 3, testing and perplexity. Or, as I like to think of it, measuring the surprise. Okay, so once we've built our model using those simple fractions, we absolutely have to evaluate it using a separate, held-out test dataset. We need to make sure it hasn't just perfectly memorized the training data, because if we test it on the data it already learned from, it's essentially taking an open book test, which tells us nothing. So we evaluate its true performance using a metric called perplexity. Without getting bogged down in the formulas, you can simply think of perplexity as how surprised the model is by the very next word it encounters.
Minimizing perplexity is the ultimate goal here. A lower perplexity means the model is getting really good at guessing the upcoming text. It's rarely surprised by the data it sees because the language is highly predictable. That means there's a lower branching factor or fewer realistic options for the next word. On the flip side, a high perplexity means the language is wild and unpredictable. The branching factor is high, and the model is just constantly shocked by what comes next. Let's look at a real example to see what happens when we actually generate text. Check out this absolute gibberish. To him swallowed, confess here both. This was generated by a unigram model trained on the works of Shakespeare. Because a unigram predicts the next word without looking at any previous context at all, it just spits out words proportional to how often Shakespeare used them overall, zero regard for actual sentence structure. But when we upgrade to a 4-gram model trained on that same Shakespeare data, it outputs perfectly coherent phrases like, "It cannot be but so." Actually, scratch that. This reveals a massive danger called overfitting. The model didn't learn to speak like Shakespeare, it simply regurgitated a direct, exact quote from the play King John. Why? Because its memory matrix was too sparse.
There weren't enough unique four-word combinations in Shakespeare's limited text, so the model just memorized chunks instead of learning to genuinely generate new language.
Now this is really interesting. If you read this financial-sounding text, you'll see it was generated by a trigram model trained on the Wall Street Journal. This proves that these models are heavily dependent on their specific training corpus and cannot easily generalize to new genres. A model trained on 1980s financial news has absolutely no idea how to speak like Shakespeare, and vice versa. It only knows its own world.
All right, part 4, the zero problem. How we deal with the unseen.
So we now know how to count n-grams and measure our success. But we hit another huge roadblock when our test set includes perfectly acceptable English phrases that just happen to never appear in our training data. Take a look at these raw bigram counts from a data set called the Berkeley Restaurant Project. The data is absolutely dominated by zeros, and that is disastrous. Because when you're multiplying fractions to get a final probability, a single zero-count word combination drops the probability of the entire test sentence to 0. It effectively tells the model that a perfectly normal sentence is mathematically impossible just because it hasn't seen it yet.
Which leads us to our final section, part 5, smoothing the probabilities, or shaving off probability mass. To solve this sparsity issue, we use techniques called smoothing. I like to think of it as playing Robin Hood with math. We basically shave off a tiny bit of probability mass from the rich, frequent events in our data, and we redistribute it to the poor, unseen, zero-count events. We have a whole arsenal of smoothing algorithms at our disposal to fix this zero problem, ranging from simple addition to complex context weighting. Let's look at how a couple of these actually work in practice.
First up, Laplace smoothing. It is by far the simplest fix. You literally just add 1 to every single count, turning all those zeros into ones. But because it adds 1 to every single zero in a massive vocabulary, it ends up stealing way too much probability mass from our legitimately frequent word pairings. It's just a bit too much of a blunt instrument. It aggressively distorts the real probabilities just to get rid of the zeros.
So, a much more elegant solution is interpolation. With interpolation, if we haven't seen a specific three-word phrase, we don't panic. We just safely rely a little bit on the two-word phrase to generalize and fill in the gaps. We're basically mixing our different n-grams together, relying on the smaller, more common chunks to inform the larger, rarer chunks.
But honestly, out in the real world, with massive practical applications, engineers often use a technique with the wonderful name stupid backoff. And it does exactly what it sounds like. It completely abandons perfect math and simply drops down or backs off to a smaller word chunk if the larger chunk is missing. It gives up on being a true, pure mathematical probability distribution, but it's incredibly fast to compute, and it works exceptionally well when you have huge amounts of data.
Which leaves us with a really fascinating final thought to take away from this explainer. If our language models are fundamentally just predicting the next word based on the historical training data they've consumed, as we keep scaling these models up, what lies beyond the limits of that data? When they finally ingest the entire internet and run out of human history to read, what happens next? It is definitely something to think about as we watch this incredible technology evolve. Thank you so much for joining me today, and keep learning.